Hey guys, welcome to our lesson on synthetic substitution and ultimately synthetic division. Before we get into synthetic division, we're going to do an exploration called evaluating a polynomial function using synthetic substitution. Now, first, let's review what just run-of-the-mill normal substitution is. It'd be a problem like we have here, given p of x equals 4x cubed plus 3x squared plus 2x plus 1, find p of negative 2. Now, we've done this many times. That means we just plug negative 2 in for every x value and then do the simplifying to get our output value. So when I put negative 2 in for every x value, right there, I have 4 times negative 2 cubed plus 3 times negative 2 squared plus 2 times negative 2 plus 1. Negative 2 cubed is a negative 8. Negative 2 squared is a positive 4. Oops. And then actually, if I take a 2 times a negative 2, I'm going to get a negative 4 and then plus 1. So this is going to end up allowing us to take negative 32 plus 12 minus 4 plus 1. And we should get out negative 23. So p of negative 2 equals negative 23. This is our input, negative 2, and our output is negative 23. Okay. You can set up an array of numbers that captures the sequence of multiplications and additions needed to find p of a. Using this array to find p of a is called synthetic substitution. So when it says captures the sequence of multiplications and additions, you can see up here in my work, this is all multiplication. When I'm cubing negative 2, I'm multiplying by itself 3 times. And this one, I'm multiplying negative 2 by itself 2 times. Then this is multiplication. And then this last series is addition. Okay? So all of those operations can be done synthetically, which synthetic in my mind, I think of fake or not real, okay? So using kind of a shortcut method, which we call synthetic substitution. So given the same polynomial, p of x equals 4x cubed plus 3x squared plus 2x plus 1, find p of negative 2. Same instructions, but it says using synthetic substitution. So let me show you the setup before I explain the process. We have a little box right here that we put in negative 2. That's obviously our input value. That's what we are substituting. So that would be our a value. As you see, that's what the letter we're using there. Okay, then these numbers up here. Take note, those are the coefficients of our polynomial function that's written in standard form. So we do need to make sure our polynomial function is in standard form. And then what we do to get started is we bring down our first 4, our first coefficient, and that's where we start right here. And every diagonal arrow following that means we take this number down here and we multiply it times our input, our a value up here, negative 2. So 4 times negative 2 gives me negative 8. And then the arrow coming down, we add. 3 plus a negative 8 is a negative 5. We do multiplication again. Negative 5 times negative 2 gives me a positive 10. And we add. 2 plus 10 gives me 12. And then we have one more diagonal arrow to 12 times negative 2 is negative 24, and then we add 1 plus a negative 24, and that gives us negative 23. So we have this an array of numbers on the bottom, and it asks us here, what does your final number represent? This negative 23. Isn't that what we got as our output using just normal substitution? And it certainly is. So what does it represent? That is our output value when negative 2 is substituted. So we have p of negative 2 equals negative 23. All right, so synthetic substitution, as you can see, once you get the process, it's going to be much more efficient maybe than just doing regular substitution. The great thing about synthetic substitution is what we're going to find out right here. There is an interesting relationship between synthetic substitution and long division of polynomials. Let's figure it out. given the polynomial p of x equals 3x cubed plus 4x squared plus 10, first divide p of x by x minus 2 using long division. So I'm going to do that over here. I have x minus 2. And then I'm going to write 3x cubed plus 4x squared. I'm going to put a placeholder here for my x term plus 0x and then plus 10. All right, what do I multiply times x to get 3x cubed? That is going to be 3x squared. And then 3x squared times x is 3x cubed. And 3x squared times a negative 2 is negative 6x squared. And then I subtract those. And my first terms cancel. Then I have 4x squared plus 6x squared gives me 10x squared. And I bring down my remaining terms. Plus 0x plus 10. Okay, what do I multiply times x to get 10x squared? 10x. So that's 10x squared, and 10x times a negative 2 is negative 20x. I subtract these two terms, and my 10x squareds cancel, and I have a positive 20x plus 10. And we ask ourselves one last time, what do I multiply times x to get 20x? That would be just plain old 20x, and then 2 times 20 is a negative 2 times 20, is negative 40. I subtract, which changes that to a positive 40. My 20x's cancel, and I have a remainder of 50. So writing my solution as my quotient, 3x squared plus 10x plus 20 plus my remainder 50 over my divisor, x minus 2. Okay, so that is what we get when we do long division. Now it says, use synthetic substitution to find p of 2. All right, so I'm going to put 2. Oh, excuse me. How did that happen? In my little box up here, and I'm going to put my array of coefficients of my polynomial, which are going to be 3. And then I had 4. And we put a placeholder in long division. We do that in synthetic substitution as well. And so 0 and then 10. Remember, I bring down my first number. And I multiply every number on the bottom times my input, which is 2. So 3 times 2 is 6. And then I add 4 plus 6, and I get 10. Now I go 2 times 10, and I get 20. And I add 0 plus 20, and I get 20. And then I take 20 times 2, and I get 40. And I add 10 plus 40, and I get 50. What do you notice? Well, what we should notice here is some similarities. Do you notice that my last number from synthetic substitution is 50? And that happens to be my remainder of the long division. And then hopefully you can see a relationship between the other 3 numbers in my bottom row. Those are the coefficients of my quotient. So as you can see, when I do synthetic substitution, now hold on, let's look at what I substituted in. First of all, I plugged in 2. So what is that relationship to the factor x minus 2? Well, wouldn't the value of 2 make this equal 0? So 2 is the 0 value of the factor. So, or just take the opposite sign. So x minus 2, if I wanted to do synthetic substitution, I plug in a positive 2. And then what happens when I do that, the first values give you your coefficients of your quotient, and the last number gives you your remainder, which is stated right here on the next page for us. So what we figured out, there are 2 important things to notice, is that P of A, which is our output, right, in our synthetic substitution, is equal to the remainder when P of X is divided by X minus A. So here's X minus A, here's A. So these are the same, right? Okay, the other thing is that the numbers to the left of P of A, which would be these 3 numbers, give the coefficients of the quotient right there. Okay, so because of this, synthetic substitution is also called synthetic division. So we can use those terms interchangeably. So understand that we can use this process for substitution or division. All right, we're going to do a couple examples. Synthetic division. I can use synthetic division to divide polynomials. Given a polynomial p of x, use synthetic division to divide by x minus a and obtain the quotient and a non-zero remainder. Write the result in the form quotient plus remainder over x minus a, as we always do. All right, so one thing about synthetic division, however, as you notice, I specifically am dividing by this x minus a. We can only use synthetic division when we have a linear polynomial like that. So we can't have like an x squared or an x cubed to divide by. So here we go. Remember that when we're dividing by this factor, we find what would make that factor equal 0, and that's what we actually plug in. So we're going to actually plug in 4. We're dividing 2x cubed minus 7x squared minus 8x plus 17. So we list the coefficients, making sure that it's in standard form and we're not missing any terms. And this one we are good. We bring down the first number and we start our multiplication by our input value, which is 4. So 2 times 4 is 8. Negative 7 plus 8 is 1. Okay, 1 times 4 is 4. Negative 8 plus 4 is negative 4. Negative 4 times 4 is negative 16. And 17 plus a negative 16 is a positive 1, which is our remainder. So we are dividing a cubic by a linear. So if we think about that, our first exponent on our quotient would be squared. Okay, and it should always go down from there. And our last term would be our constant term. So we write our answer as 2x squared plus x minus 4 plus 1 over x minus 4. All right, let's try B. We have 4x to the 4th plus 7x minus 3x squared plus 2 divided by x minus 1/2. So the first thing I'm going to do is I'm going to put a positive 1/2 in my box. Then I'm going to make sure my polynomial is written in standard form, which this one is not, so I'm going to do that. That's going to be 4x to the 4th. I don't have a cube term, so it'll be 0x cubed, then minus 3x squared plus 7x plus 2. So the coefficients I'm going to list out are 4, 0, negative 3, 7, and positive 2. Bring down my 4. So I'm multiplying all these numbers by 1/2. When you multiply something by 1/2, it's the same thing as dividing by 2. So I can think, what's 4 times 1/2, or half of 4 divided by 2 is 2. 0 plus 2 is 2. What's half of 2? 1. Negative 3 plus 1 is negative 2. What's half of negative 2? Negative 1. 7 plus a negative 1 is a positive 6. And half of 6 is 3. 2 plus 3 is 5. So we have done our work. We know our remainder. We had a degree 4 polynomial, which means our quotient is going to be degree 3. So we're going to have 4x cubed plus 2x squared minus 2x plus 6 plus our remainder 5 over x minus 1/2. Okay, we will do the next 2 examples in class tomorrow. Have a great night.